This is part of a series of videos that introduce the niche mapper R-Shiny web applications. Um, I've already introduced these apps in general, so I'm going to go to the page that has all the apps. I've already introduced the microclimate model in general and the ectotherm model in general, using global databases. But this video introduces the apps that are using Australia-specific and US-specific databases. So I'll first go to the US one. So there's a US microclimate model called the US Soil Microclimate Hindcaster. This one is using the GridMet dataset, which is developed by John Abbotsoglu and his group, and it goes back to 1980, and it's a daily climatology. And it goes up to present, so this is directly querying that dataset through the OpenDAP method, so it's always up to date. And the starting location is near Mount Rainier in Washington. You can see it's quite a cold place, and you can see the prediction here is that it would be covered in snow up until about June. That's this grey blob here, and then the soil warms up, and then the snow would come back in about November. So this is the soil temperature plot as with the previous apps, and you've also got all the other plots as before, other microclimatic plots, and the soil moisture plot at the bottom. And again, you can download all the results just as before, choose any particular place or year that you like. And then there's the ectotherm hindcaster, which is just the ectotherm model again, but applied to that GridMet dataset. So running the microclimate model and then the ectotherm model. And it starts off at a place called Eagle Lake in California. And the reason that starts there is historical. This paper here by Ray Huey, Chuck Peterson, Steve Arnold, and Warren Porter, called Hot Rocks and Not So Hot Rocks, about the way garter snakes use rocks as retreat sites to thermoregulate when they're inactive. It was this paper actually that got me connected with Warren Porter and using these biophysical models. And if we go down to their figures here, on the 28th of July in 1983, they made measurements of soil temperatures at this site at different depths, 2.5 centimeters, 5, 15, and 50 centimeters. And they also measured the temperature of a cropper model mimicking the properties of a garter snake out in the open as well. So if we go back to this app, I've actually run the simulation for the animal not thermoregulating, but basically the operative temperature, an inanimate object just sitting out in the open. And if we go to July the 28th, you can see the prediction of the operative temperature. And it's predicted to go from a low of about 5 degrees at night up to about 50 degrees during the day on this particular day in July at Eagle Lake. And if we go back to the plot, you can see it goes from about 5 degrees up to about 50 degrees. You can see the effect of intermittent cloud cover here in this figure, which you're not capturing here because it's a daily climatology. It doesn't really know how the solar radiation varied through the day, but nonetheless, a pretty close prediction. And if we go down to the soil temperatures, these are those same depths, predictions of soil temperature at the same depths as in this figure 2C. And you can see that 2.5 centimeter depth temperature goes up to about 40 in the middle of the day, or at about 3 o'clock, I should say, and down to about 12 degrees at dawn, or just past dawn. And you can see we've got from about 10 degrees up to about 40. So very similar. The temperature at 15 centimeters is going from just above 20 down to about 17 and up to about 25. Here it's going from about 25 down to about 20 and up to about 25 again. So really close. So that's they're the apps for the US, and then we've got the equivalent apps for Australia, the soil and ectotherm model. For Australia, these are running off a data set called the Australian Gridded Climate Dataset, AGCD, also known as the Australian Water Availability Project in the past. It's a 5-kilometre resolution data set. The details of it are in Jones and colleagues' paper. It also uses near-surface wind speed data set developed by McVicker. And it goes back to 1911, and it's again a daily gridded data set. It's got daily rainfall, it's got daily maximum and minimum air temperature. They all go back to 1911. It's also got vapor pressure going back to 1971 and total solar radiation going back to 1990. And I've put some crude multiple regressions in there to estimate the variables that are missing based on their relationships with the other variables for the time when we have all the variables. And that does a pretty good job of inferring the missing variables, the missing vapor pressure or solar radiation. So you can actually take this back in time to 1911 and make predictions across Australia. And we've got the ectotherm model as well. And both of these are just starting off as a default location. The same location is just behind me in my Zoom background. It's a place in the middle of nowhere, northwest of Alice Springs in Central Australia. And so with the ectotherm model, you can see shortly what the body temperatures of a lizard would be out there. If it was thermoregulating, how much shade it would use, how deep it would need to go, the activity window. You can see that it would actually have to seek shelter in a burrow and stop being active at certain times of the day because it's so hot in the middle of summer in this location. Note also that both of the Microclimate app and the ectotherm app allow you to choose the ERA 5 data set as well as this AGCD data set. And I have that ERA 5 data for Australia from 1979 up until October 2022. So different time windows for those two different data sets, but overlap. Their combined time span is quite a large time span, 1911 to 2022. So those are the Australia and US specific apps, and these will allow you to make quite accurate predictions for those particular parts of the world. But of course, you can always use the global hindcaster, which uses the NSET data and the ERA 5 data, and you'll get reasonably good predictions from those as well.